everyone, this is IGCSE on fingertips, and from this video you will be able to see paper 6 of physics and chemistry grade 10 on our channel. Let's do the first paper. Let's get started. It's paper 6-1 of October-November 2021, right? It's the most recent one. So let's start with this question. So you have question 1, a student investigates the stretching of a spring. Okay, figure 1.1 shows the apparatus. Okay, this is 0 centimeter mark, and these are the spring and meter rule. Okay, the meter rule is clamped in position near to the spring, like they have shown. Write down the scale of readings in mm from the meter rule at the top and bottom of the spring as shown in figure 1.1. So this figure is showing us that where is the starting and ending of the spring. Okay, so what we shall do is, see, it's a centimeter, right? It's 1 meter rule which has marking in centimeter, and we need answers in mm. So let's first notice what is this measurement. So there are 10 divisions, right? From 44 to 45 there are 10 divisions. So this must be 44 minus, there are 10 divisions. So this is 44.1, 44.2, 3 and so on and so forth, right? So minus 0.1. So this will be 43.9. Writing it in mm, you should write 439. In the same manner, this is 45.1, 2, 3 and 4 multiplied by 10. Because it is in mm, so you have 454 mm, right? Now let's see what are they asking more. Using the two readings, calculate the length L0 of the spring in mm. So what will be the length of the spring? The difference between these two, right? I find the difference between these two is 15 mm, correct. Now record L0 in table 1.1. The value L0 is the length of the spring when the load L0 is equal to 0.00 Newton, right? Now where is this table? This table is here. Okay, sorry, this table is somewhere here. So how much is it? This is 15 mm, correct? This is 15 mm. Let's see what is the next question here. We have the student suspends a load 0.2 Newton from the spring. He records the new length of the spring. Use the equation E extension is equal to L minus L0 to calculate the extension of the spring. Record the value of E in table 1.1. So now see, the initial length of the spring is only 15, right? So it gets 17. So what is the stretching? The stretching in the spring is for 2 millimeter, correct? Now let's see the next question. Okay, complete the extension column heading in table 1.1. So what should you write here? See, if the length is in mm and therefore the difference will also be in mm. So I will write extension in mm. Okay, it is the unit. Now student repeats the procedure using loads 0.40 Newton, 0.60 Newton, 0.80 Newton and 1 Newton. He records the readings and results in table 1.1 as they have shown. So 5 is 20 minus 15, 8 is 23 minus 15, so on and so forth. He's found out the extension and the load and the length of the spring is given. Okay, what's next? Plot a graph of extension in mm on y-axis against load in Newton on x-axis, right? Load in Newton on x-axis. So what will be the first thing that you do? The first thing, let me just get to the graph that I have drawn for you, right? I've already did this with pen and paper, right? To save us some time. So the first thing you would do is mark that extension is on y-axis, load is on x-axis in Newton and in mm. This should score you the first mark. Taking a scale in such a way that at least half of the graph is covered should score you the second mark, right? drawing the line accurately should get you the 3rd mark, and the best fit line should get you the 4th mark of this graph, right? I have drawn the line already. Your best fit line may differ a little, but remember, this is the starting point, right? They have said that at 0 load, the extension in spring is 0. So in this graph particularly, it should touch 0, 0, and that is why a graph must start with 0. Okay? Let's go to the next part of the question. So, just a second, we have part D. Figure 1.2 shows the unstretched spring and the spring with the load. On figure 1.2, show clearly distances L0, L and E. So the initial length, the extended length and the extension, right? So what I'll do, I'll just show it here that from the starting of the spring to the ending of the spring, this is L0, right? Please use a scale, draw a straight and clear line to show that this much is L0. This much should be L, right? This is the extended length, and the difference between these two, right? The difference between these two is nothing but extension. So you can extend a line from here and draw a gap between these two, showing that this is the extension of the spring, right? Then I think that question is done. Yes. So you have the second question. A student investigates the resistances of resistor in different circuit arrangements. Okay. Figure 2.1 shows the first circuit arrangement: power, resistor, another resistor, voltmeter and ammeter. She measures the potential difference PD Vx across the resistor X and the current Ix in the circuit, right? They are in series. Both of the resistor will have same current. The meters are shown in figure 2.2 and 2.3. So let's see, right? Okay. Now write down the readings. Include the units of potential difference, current or resistance where appropriate in all parts of the question. So voltmeter is going to measure voltage. It has 5 units, right? Sorry, 5 division between 2 units. So for each division is 0.2 units, right? How do I know that? Simply, if there are 5 units for each division, right? So 1 by 5. This will give you 0.2 is the each division. So the first reading is 1.2. So voltage is 1.2 volts, right? Clearly written, include the units. Then here you have 10 divisions. Do you? No, you don't, because this is 0.3, right? So again, the same logic applies here, but 0.22, 0.24 and 0.26. So the current is 0.26, and we know ammeter measures the current, right? So you have 0.26 ampere and 1.2 volt. Calculate Rx, the resistance of the resistor X, using equation given. So you can simply write 1.2 upon 0.26, right? The maximum significant figures we have is 2. So I will round off my answer to 4.6 ohm, right? Ohm is the unit of resistance. Let's find the next question we have. The student connects the voltmeter to record Vxy, right? So I'll just draw a rough arrangement. So what he does is, he had some arrangement like this, okay? There were 2 resistors here. So he measured the voltage across both of them, right? The potential difference across the 2 resistors, she calculates Rxy, the combined resistance of resistors X and Y connected in series is given. So from the same method, what did they do? They measure the voltage. Now the current across both of them is same. So they therefore find the total resistance, out of which they subtract Rx, and therefore they find Ry, which is 5.78. They are asking, state and explain whether Rx, which was 4.6, and Ry can be considered to be equal within the limits of experimental accuracy. Obviously, no, the values are too different, right? The difference is too much, the value are too different. This is our answer. Then we have the student connects a resistor Z in parallel with resistor X. She connects the voltmeter to record Vxz, the voltage across X and Z. The potential difference across the parallel combination of resistor X and resistor Z. Draw the circuit diagram for this arrangement. Label the resistor X, Y and Z. So what are we doing there? Again, the same thing is happening. There is a power supply, right? And then there is a resistor which is X, right? Then they are adding the resistor Z here, right? And then resistor Y was already present in parallel, correct? They are measuring voltage across both of these. So I will add a voltmeter in parallel, write V here, correct? So this is our arrangement. Let's check that except this RZ, does the arrangement match? Because it is done in the same arrangement, right? In the same situation. No, there is an ammeter and there is a switch. So let's do that. Let's add our ammeter and let's add our switch. Okay. So make sure every time you do these type of questions to check again, because they will be on different pages most of the time, right? You should reproduce the same image, because if you want to find out Rxz, you will need the current. So this is your complete diagram. Part B, student records Vxz, the potential difference across the two resistors in parallel, and Ixz, the current in the circuit. Calculate Rxz, the combined resistance of the resistor connected in parallel using R is equal to V by I. So the values have already been given. So R should be equal to 0.8 upon 0.36, right? V by I. So 0.8 upon 0.36 should give you 2.2 ohm, right? Same significant figures must be carried. So 2.2 ohm. Next, another student does this same experiment using a set of 3 identical resistors. Identical meaning same resistance. Maybe 4 ohms, maybe 8 ohms, maybe 20 ohms, we don't know. His results show that within the limits of experimental accuracy, the combined resistance of the 2 identical resistors connected in series is 4 times the combined resistance of the same 2 resistors in parallel. So he is essentially saying that Rp, the resistance in parallel, right, is 1/4 of the resistance in series. Okay, if 2 resistors of same resistance are made parallel and series. Okay. To test whether his results are true for other values of resistance, he does the same procedure with other sets of 3 identical resistors. Suggest the value of resistance he could use to reach a conclusion during a 1-hour practical lesson. So if it's a 1-hour practical lesson, the resistance must be low, not 100, 200, 300. That will take time because the fluctuations will be larger. When the resistance is very high, given the power supply, you might have very low current, and therefore because of the resistance you may get a very fluctuating value. So we'll take resistance in smaller values, right? Now I know it must be divisible by 4. To make his job easy, what I will do, I'll ask him to take a 2 ohm resistor, I'll ask him to take 5 ohm resistor, and I'll ask him to take a 10 ohm resistor, right? These addition and this reciprocal addition for parallel, it will be easier for both the jobs, right? So I will suggest 2, 5 and 10 ohm he can use. Okay, we just have to suggest the values and nothing else. Moving on to the next question, right? The question has changed. A student investigates the position of the image in a plane mirror. Figure 3.1 shows the ray trace sheet. Okay, we have to draw something here most probably, right? and I've drawn it for you as well. Again, I'll zoom it down so we can see what is happening. Okay, here are the questions and here is my answer. Part A on figure 3.1, right? Draw a normal to MR that passes through its center. So I'll measure whatever this is and with the ruler draw a normal. Normal meaning it is at 90 degree. It is NL must be perpendicular to MR. Label the point at which NL crosses MR as B. Now as you can see, I have labeled this point as B. Okay. Next, draw 7 centimeter long. Draw a line 7 centimeter long from B at an angle of incidence I is equal to 70 degree to the normal below MR and on left hand side of normal. So on this side of normal, right, as you can see here, what I have done, I have drawn this line, right, I have taken this point A, drawn that line, right. So what I had done, I had to measure that this angle must be 70 degree, right, that is the angle of incidence between normal and a ray. Name it AB, that's what they have said. So I have named it AB. Let's go back. Draw another line 7 centimeter long from B, okay, at an angle of theta equals to 40 degree. So in the same figure, this must be 40 degree, okay. To the normal, again below MR and again on the left hand side, name the end point as C. So that's what I have done. Let me quickly show that to you, right? So this is C, B, this angle is 40 and it's a straight line of about 7 centimeter, okay? Right. Now, mark two neat crosses, positions for two pins P1 and P2 on line AB at a suitable distance apart for this type of ray trace experiment. So what you have to do, you have to mark 2 points. They have marked P3, P4, P5, P6, right? So you have to mark 2 points in such a way to show that the ray is passing through that. Now there is only one line that can pass through 2 points, right? So that will give us a perfect ray diagram. But if you notice, they have kept some distance between P3 and P4. And in fact P5 and P6. So you can measure this distance with your scale and mark your points P1 and P2, right? Mark your points P2 and P1 in this manner with the same distance, okay? Then what do we have next? They are asking, the student places a plane mirror on the line MR, right? So let's go back. We'll need a little bit of back and forth for this question. So MR, they've kept the mirror like this, okay? And what is happening? What is happening is that he places two pins P3 and P4 so that P3 and P4, the images of P1 and P2 all appear exactly one behind another. So he is keeping the mirror here, viewing from here, and it appears that P1, P2, P3 and P4, all the 4 pins, they actually meet each other. Okay? They actually meet each other. They appear to be in straight line of his vision. Okay? Now, measure the angle alpha. Draw a line through the positions of P3 and P4. Continue the line until it meets MR. And measure the angle alpha between the line and the normal NL between MR, include the unit. So what we have to do, we have to measure this angle alpha, right? First draw this line P3, P4 and make it meet B. And then draw this alpha, right? This is our alpha. Now when I found out the value of alpha, it is the angle of reflection, right? Now by understanding and by knowing the angle of reflection, I knew alpha was 70, but you have to measure it, right? I did find alpha was 70. For me, 70 degree include the unit. Okay. Then you have the student places reflecting face of the mirror vertically on the line AB with the center of mirror at B. Right. So let me just give you a rough diagram that instead of this line, he places mirror here, and then the experiment continues. He places pin P1 and P2 on line CB, places pins P5 and P6 so that the pins P5 and P6 and images of P1 P2 all appear exactly one behind another. Same thing what he did for P3 and P4. Draw a line through positions P5 and P6, continue the line until it meets NL. Measure the angle beta between NL below MR, include the unit. So again, now let's go back to our diagram. So what are they asking? They are asking first P5 and P6, you draw this P5 and P6, make it meet B, right? He had kept the mirror here. Instead of this, he had changed the position of the mirror and kept it here. Now it appears, okay, so what he did, he placed pins here and it appeared that these pins were in alignment with P5 and P6. They want you to measure beta, okay. For me, beta comes to 80. It should logically come to 80 because the angle is shifted by 40 degrees. So your other angle also will be shifted by 40. Beta should come to 80 degree, right? Pure measurement, even if you don't apply any logic, pure measurement, you should get answer 80. A student investigates a possible relationship between angles alpha and beta. The angle theta remains constant at theta is equal to 40. So the bending of the mirror, it remains at 40. Okay. Suggest values of the angle of incidence that he could use. So see, what he should use is that a range of values, right? So I will suggest, because you get alpha 70, right? So I will suggest values of, let's say, 75, 80 and 85. Three values should do. So 75 degree, 80 degree and 85 degree. Okay. A student does this experiment with care. Suggest one practical reason why the result may not be exactly those that the theory of reflection predicts, because he has not placed, the base of pins properly, right? He has done some systematic error. That is why he is getting this wrong answer pins properly, right? Then next you have tick the boxes that indicate relevant precautions that the student should take with this type of ray trace experiment. Carry out the experiment in a darkened room. Yes, he should. Draw thin lines. That's okay. Keep one eye closed to avoid parallax error. Keep room temperature constant. Not required. Not a thermal experiment. View the bases of the pin. Yes, not the tops, because that can cause a error. Right? That's the end of the question. We have next question. So question 4. A student investigates the time taken to heat water in different uninsulated containers. The containers all have same volume and shape. Okay. The water is heated with an electric immersion heater. Okay. The following apparatus are available. Selection of containers. So different. If they have same shape and volume. Okay. So different container material maybe. Right. Thermometer is available. Supply of cold water. Immersion heater with power supply. Plan an experiment to investigate the time taken to heat water in different uninsulated containers. Right. So you have different material contained. List any additional apparatus that is required. I will require stopwatch. So I am making notes, right? Not writing the answer. I require a stopwatch. Correct? Then explain briefly how would you carry out this investigation. Okay. So okay, we will write that. I think that is when we will plan this whole experiment. State the key variables that you would keep constant. Delta, theta, right? The change in temperature, the range of temperature. I will also write theta 1 and theta 2, right? Their starting temperatures and their ending temperatures, and therefore the difference in temperatures must be equal. Draw a table or tables with column headings to show how would you display your reading. Okay, so what I'll do, I'll write here in a table material and time taken for the change in temperature. The time taken will be in seconds. We will draw that table in better way, just giving you an idea. Explain briefly how would you use your readings to reach a conclusion. You can draw a graph, and from the slope you can say it's directly proportional, inversely proportional, or not proportional at all, right? So let's start our experiment, right? Do they want anything else? No, they don't. So let's start our experiment here. So what shall we do? So we will need stopwatch, right? That is what you have to write. We will need stopwatch. Okay? Take 4 different types of container, correct? That is what you should do. Right. Now the next step is how to plan this experiment. So basically what I want to do is I'll take a container, okay, and add a fixed equal amount of volume, right, in each container. Do we have a measuring cylinder for this? Let us check. Measuring cylinder, yes. Okay. So what I'll do, I'll add equal amount of water in each container. Check the temperature, the initial temperature of each container which contains water, right? The initial temperature of water. It must be same. And then I will add immersion heater. I'll put an immersion heater and heat it to a range of, let's say, 70 degrees. So if I start at 25, I'll end at 95. I'll continuously check the thermometer, and then that is what I will do, right? Now I have to record the time when I start and then again when I stop. Okay? Repeat this procedure twice. Take an average of that, right? Repeat this, taking average and taking the thermometer measurement and everything for different containers, right? At least 4 containers, right? Then we will record the values, that which material required how much time for the same change in temperature, right? And then if you make a graph and if you find that the line is a straight increasing slope, then it's directly proportional. If it's a straight line with decreasing slope, it's inversely proportional, right? But expectedly it should be directly proportional, or it should not have any relationship, right? So take 4 different types of container, add equal volume of water in each container and measure temperature of water for each container. This must be same, right? Put immerse the heater, I'll say, right? Immerse the heater and let water heat for up to delta theta 70 degree Celsius, right? Start the stopwatch when you start heating and stop it when you stop heating. Record the time it took to cause this temperature change, right? repeat the same for better, same with same experiment, or I should say procedure, right? Okay, let's write that. Repeat the same procedure again for same container to average the results, right? Which will increase your accuracy. Again, repeat the procedure for each container, right? Make a table of results as follows. Okay, so what are the results of this? So you have a material, right? Delta theta will be same for all of them, but still let's record it for our understanding. And time taken, which is in seconds, right? Do not forget to write units wherever applicable, okay? Otherwise you will not get marks for showing this table. Now it does not matter if we put the values or not, because we are not doing the experiment, we are planning it, right? Then how would you conclude? Draw a graph draw a graph between type of material and time taken to find a correlation, right? That is the end of answer and the end of paper. Thank you for watching and come back for more videos.